my own project, and it was compiling slowly, as you know, sometimes the Scala compiler is known to do. And I thought, oh, I'll profile it, see what's going on. I'm like, what? This is crazy. And I found a line of code, and I'm like, this is crazy. And I went to look to the code, and I checked it out, and I'm like, huh, I can fix this. It's easy. So that 2 and a bit years ago started my adventure in playing inside the Scala compiler. And I went, let's be frank, down the rabbit hole. So, how do we make things faster? It's easy. There are 3 basic rules. The first one, do less stuff. The second one, do the same stuff, but do it faster. Or the third one, as Julian will, I'm sure, back me up, is to do it in parallel. This sounds trope, I know. But this is fundamentally it. If you want to make anything faster, you've got to do one of these 3 things. So I'm going to talk today about my experiments in doing exactly this. And my clicker doesn't work. There we go. So it's probably worth saying that a lot of the work that I've been doing, I've been using a test project to keep everything consistent, and I use Actor because it's a nice general Scala project that everybody knows. It's not too big, and it's about, to give you a clue, it's about 36,000 lines of fairly normal Scala code. And on my machine, it will compile consistently in about 6.5 seconds. But today, I'm going to focus mainly on object allocation, because I've found there's a fairly high correlation between object allocation and speed. The lower the object allocation, the faster your code goes. Now, it's not exact, but I always find that places that are allocating objects are a good hint about where your compiler is spending time, because if you just pick up a profiler and run it, you'll find it's actually very hard to work out exactly what the best bit to optimize is. And there's whole talks on how profilers actually lie to you on a regular basis. So I want you to think, I'm compiling Actor, 36,000 lines of code. What is the most? There's going to be, it's not quite as cool as Julian's audience interaction. I don't have an app or anything, but I do have some questions. What's the most allocated object when you're compiling Actor with ScalaC 2.12.5? You want to make a guess? Boxed unit. It's not boxed unit. Any other guesses? Cons. Come on. Cons. Excellent choice. 10% of the entire of every single object in a compilation is cons. And if you didn't see it already, anybody want to guess what the second highest one is? String? It's not string. It's a good guess though. Char arrays. And then sum, and then string. So the interesting thing is 25% of the allocation so far, and we've yet to hit a single class that comes from ScalaC itself. Does anyone guess how far down the list I have to go before I hit a ScalaC object? 8? Excellent, good guess. The answer is, in fact, this clicker is really not working today. Go back to the old-fashioned way, the keyboard. So, the first one is part of the tree, as you might expect. But there's a bunch of interesting stuff here. Oh, no. You've broken my display. Right. So there's a few interesting items here. I can point and use a keyboard. It's all good. So the highest object in the Scala compiler, other than sort of core classes, is tree info, which is not unexpected. But it only counts for just over 1.5% of the object allocation. And in fact, I've reached 30% of the objects before I've got to anything related to Scala C. There's a few other interesting things here which I'm going to come back to. Object ref, array ops of ref, string builders and name ops. So I've been fiddling with this stuff along with a bunch of other people for a while. Anybody that's been here before has probably heard me wittering on about it before. Julian's nodding in sadness, I think. So in 2.12.5, we allocate a total of 75 million objects. How does that compare against 2.12.1? I don't have 2.11.9 stats here. And the answer is, I actually consider it pretty good. We've reduced the object allocation from 90 million objects down to 75 million objects. You can see the cons is improvement there. Depth is an interesting one. We're going to come back to that one. As we are with list buffers. Object refs are where you have a closure and you have to pass in a reference to the outer scope. So there's some interesting stuff there. In each of these cases, what tends to happen, or how this has occurred, is you put a profiler on it, you look at what's being allocated, you find interesting places, and you fix them. And you're not going to get a 50% speed up by changing one bit of code. Right? If that was there, the Scala compiler team would have done it already. Right? This would be a no-brainer. What you get is a lot of incremental little changes that build up to bigger changes. And between 2.12.1 and 2.12.5, the Scala compiler has sped up, depending on who you speak to, between 20 and 30%. And I think that's pretty good going, to be honest, on a mature project. So let's talk about immutable.List. It's one of my favorite classes, and it's not immutable at all. So, as you can see, there's a nice var right in the middle. It's fairly easy to spot. This is one of those fights between the pure functional world and the optimization world, which is, when you think about building a list, when I do a map on a list, I start from the head and I work through, which is really good. We're really good at doing that, right? I deal with the head object, I go to the tail, and I continue doing that. The problem is the result list. If I want to do it without any mutation, I have to build the list from the tail. I have to go to the tail and append the head and append the head and append the head. And to do that efficiently, I'd either have to push everything onto a stack and then pop it and build the list, or I can cheat. And in fact, this is when you see list builder, that's exactly what it's doing behind the scenes. So a lot of the methods in the standard collections will create a list builder, iterate the list, and each time they handle an object, they will then add it to the list builder. And the list builder does an internal cheat. What it does is it builds a tail. And you might think, but this is broken, right? This is fundamentally just broken the Scala language. But it's controlled mutation. So this var is only visible inside the Scala package. You can't touch it. And in fact, by the time you ever see a list, an immutable list, it will be immutable. Nothing will ever play with it again. But it does mean, actually, you can pull some interesting tricks. Now, this was actually the first change I made. And I challenge you that everybody in the room could make these kind of changes within inside the compiler. So we all know map. This is map 4. So an immutable map starts with an empty map, map 1, map 2, map 3, map 4 to be efficient. And then, after map 4, you add an extra element, and it turns into a hash map. And the line of code that does it is this bottom one here. And when I was looking at the compile profiles, I noticed this was a hotspot. Does anyone want to guess which objects it creates and how many? Beyond, so ignoring the actual creation of the hash map part, the extra objects this method creates. So let's start. So we've got some tuples. We've got 1, 2, 3, 4, 5 tuples. This is a var args. So that means we're going to have an array, but because a var arg is actually a sequence, we're going to wrap it into an array. So above and beyond what you actually need to build the hash map, we've built 7 extra objects. Every time you do a map on a hash map bigger than 4 objects. Every time you do a filter, every time you use those objects. So a tiny change can make a huge difference. And in fact, it turned out that the hash map already had a method that instead of taking a tuple, takes a pair, takes a key and a value, and by replacing this one with this one, every single time you create a hash map, I've saved at least 7 allocations. And in fact, you save more because you have save an iterator as well. So why am I telling you this? Because this stuff isn't that hard to do. The problem is, and we'll come back to it, is that that change on its own is probably, what, 0.2% of the entire compilation speed? Because actually we've just proved in the previous slide that hashmap isn't even in the top 10. Although interestingly, tuple is. So, one of the other interesting ones I came across, and this is one of the fixes I'm most proud of, and it was a real head scratcher. What's wrong with this code? Here's depth. This is used as an internal compiler class used for keeping track of things, right? So it's an any val. It's great, right? And this is the code. Can anybody see the object allocation? Except Sam, because he's seen this slide before. Gulium can see it. So it took me quite a while. I actually had to decompile the code to work out what was going on here, because I'm not that smart. And I made this code turn from allocating 3 objects every time into allocating no objects, which is where those million depth objects disappeared to. Because whenever you do this comparison, because it's an any val, and less than is actually defined on ordered, what it would do is it would take the integer that it had in the any val, box it into a depth, call the ordered less than on it, on both sides, so it's created 2 depths, box the result, and then at the end, unbox it for you. So in fact, this is one of those changes where you've added 10 characters and removed 1 million allocations from the compiler. And that was over 1.2% of all the allocations inside the compiler. That's a fun little one. And one of my favorite, and actually one of my earliest changes, was filter and filterNot. So this is filter impl. It's quite reasonable, right? We build a little builder, which is a list builder. We iterate through and we add the ones that are removed or included in the filtered view. But I contend this code is broken in a fundamental way in terms of performance. It works. It's easy to reason about, right? We can all look at the code by inspection and have a high confidence that this code does what we think it does. But in fact, does anyone want to guess what the most common size of list is? 1, 0. So inside the Scala compiler, lots of things have lists of type parameters, lists of all sorts of stuff, and the average size is 0. The second most common case is 1. So if I call this code 1 million times with an empty list, it's going to create 1 million objects. Because at the very least, it's going to create a builder. And in fact, and what I think is worse, if I have a list where I don't filter anything out, so I take a list and the result is the same list, this code will create a clone of the original list. So where I've got beautiful structural sharing with immutable data structures, we don't do that at all. We create a second copy and use up our heap. So I'm not going to show you the code I used to fix it. Why? Because, well, for one, it doesn't fit on this slide. 2, it's ugly as sin. When I spoke earlier about the fact that sometimes you build code that I don't actually like, this is one of the examples. I like this code. It's easy to think about. But because basically you have to keep track of the head of 2 lists and then deal with the various conditions about whether or not which state you're in. And effectively you turn it into a state machine, but it's ugly. And it took a surprisingly long time to get this code, and it's just been merged into 2.13 because the fix actually breaks Mima in horrible ways. There's bigger changes that have happened. So in the back end, you can now turn on parallel bytecode generation, which speeds up a bunch of stuff there. We switched over from, now we're on Java 8, we switched over to using NIO for all the I.O. One of the interesting points about that is on Linux, it makes almost no difference. But on Windows, it actually makes a considerable amount of difference because the stack calls that Linux makes are very cheap, and on Windows, they are hugely more expensive. So you might find that whilst this isn't measured in the Lightbend statistics on the Scala compiler, the NIO change actually made quite a significant change. So I've told you that we can find changes, and I still find changes. Every time when I was writing this talk, I opened up and played with and did a new profile session, and I found more things that I could fiddle with. Right? It's one of those rabbit holes. There is bits and pieces. I'm not saying it's very clever in places. It's very good in places. But there are also bits where it's a bit like, it doesn't meet either it doesn't meet my quality standards, or from a performance point of view, I think it's weak. So I'm going to walk through one of the other changes we've been looking at. And it's this one. So this is owner chain. Owner chain is used in the compiler. It's used for a lot of things. You ask the owners of objects, the owners of a class. And what this code does is every time you call symbol.owner chain, it will create you a brand spanking new list. And the most common use case of that brand spanking new list is to check whether something exists inside it. And the worst offender I found for this is this piece of code at the bottom, which says, take the owner chain, after you create it, drop the first 2, and then do exists on it. In fact, I found one that said, instead of doing an exist, did a filter and it is non-empty. If you think about what this code is actually trying to say, it's very easy to write a method that traverses the list itself and says, does this match? So I made this change. Do you want to see the graphs of how much better it got? You ready? Did I win? So what you've got here, let's start looking at these results. So at the start, I have the cold compiler. So this is running the same Akka compilation 500 times. And I've run it 6 times. I've run 6 runs of 500 iterations. And what you see at the start is a beautiful demonstration of what the JIT does for you. So within a few cycles, and about what I find with the Scala compiler, about a minute of compilation, the compilation has gone from 22 seconds down to 6, which is phenomenal, quite frankly. But there's some weird things here. So I've got down to 6, so I'm fairly confident with my results. Except for this bit. So at some point, the JIT caught up and went, oh, I've decided to do some more work for you. And it made it 50% worse. So in one of my test runs with the new owner chain changes, or 2 of them in fact, at some point, the JIT had decided to come and help optimize my code by making it 50% slower. So do warm up your compilers, do think about what your JIT does, but be aware that sometimes it really gets it wrong. But what I'm gonna do is I'm gonna cut off the end and I'm gonna cut off the start so we can look at the low-level results. And what I want you to tell me is I'm gonna color the next slide in two primary colors. Okay. So what we've got here is we've got the baseline in blue and the optimized code in red. Now my question to all of you is, did I make it better? Yeah, that's exactly my thoughts. I don't know. Right? So the jitter you get, not jitting, but jitter in terms of randomness, is over 5%. And I'm trying to make a change where I expect the net change in total to be a maximum of 0.2%. And this has actually been one of the biggest challenges when working on the micro changes in the Scala compiler that I found. And it's one of the things I want to talk to you today about. So we're gonna wind back a bit. I'm gonna ignore the new code, and I just want to get to stable numbers on the old code. I'm gonna ignore the optimized code, and I'm just gonna plot the baseline and see if we can work out what's going on. Well, so these are the three baselines that I ran. Do you notice anything strange? Well, there's three things that I notice here. Remember, we ignored the fact that two of these runs went crazy after about 400 iterations. And I plotted the trend lines. Unfortunately, the green one's a bit hard to see, but the blue one looks really good. I'm really happy with that one. It's quite fast. The same code, not recompiled, not touched in any way, just restarted later, has run about 2% slower. So remember, I'm trying to check a 0.2% change, and I've run the same code, exactly the same code again, and I've got a 2% difference in performance. And the green line is even more fun. It's a bit hard to see, but it actually starts better than the blue one and ends worse than the red one, significantly worse, about 4% worse than the best run I've got. So I realized when I was sitting in the audience for the previous talk that maybe I should go upstairs and talk to the data people. Maybe there's some magic incantation that I need to actually turn these results into something meaningful. So I spent quite a lot of time, and in fact more time than I spent on trying to improve the compiler, on trying to build tools to help me work out whether I've actually improved the compiler. I know, it's sad, but it's what, we get rabbit-holed, right? So the idea of this is it's a bit like JMH. It's all the learnings we've put in using JMH, using iterations, repeated runs, filtering the results to try and give you good results. And the problem is JMH might be really good for small micro-optimizations. When your compile is 6 seconds, it becomes less meaningful. And I found it doesn't give you the clarity of results that we were after. And one of the beauties of this is if I'm testing with a friend of mine, I can share my test configurations, which versions of the code I'm testing, and we can baseline and run against it. These numbers, by the way, are the culmination of a couple of years of fiddling with this. I look at these numbers and they're 2% difference between two runs of exactly the same code. And these are the best I've ever got to. And to do that, you need to do a bunch of things. The first one is you need to be running on an isolated machine. Nothing else running, preferably Linux, by the way. And not a laptop. Mobile processors do a bunch of stuff to stop your machine cooking, to save battery. They will downgrade the CPU cycles. They do all sorts of things to try and help you use your laptop. But I found running a benchmark on a laptop is never as consistent as running it on a dedicated machine. You want to throttle your CPU. In fact, on most modern CPUs, your processor is already doing this for you. If you run a hot code and you get your machine really nice and warm, your processor itself will decide that it's too hot and will start down throttling your processor. Disable hyperthreading. Now this is one of those interesting ones. Does disabling hyperthreading make our numbers better? They might make them more consistent, but they also don't accurately affect what my machine does under normal use. And that's one of the challenges here. I can end up with a number which is very accurate, but it might be very accurate and very wrong. For anybody that's ever run JMH, you run your test, you write your test code, and you run it, and it seems like the code could never run that fast. Right? You change it, and it's like, this is lightning. I can't believe how fast it's coding. It turns out what's happened is the JIT's gone, this code has no value. I can erase all of it. And all you're testing is how fast you can call an empty method, and apparently, on a modern CPU, you can call that incredibly fast. SSDs, and again, the last thing I would do is you cannot test one run. What I've actually found is even running exactly the same code on the same machine with the same configuration, you can get differences of 5% between two runs of the same code. Because the JIT is not guaranteed to produce the same results every time. It's running asynchronously in the background, so sometimes it'll take one path of optimization, and depending on which level it inlines first, it might not do a different optimization. So you can find, with that and with memory layouts and all the other randomness in your machine, that even the exact same configuration, or what you believe to be the exact same configuration, can run differently on two different runs. So I'm going to narrow my focus now. We've seen the change, we've seen the results I have so far, but what I'm going to do is, with the stats in the compiler now, you can narrow it down to a given phase. So that was the entire run, 6.5 seconds of the entire run. We are just going to look at typer, because quite frankly, this code only affects typer. And here's my results. And actually, the variance is not too bad. But I've got to be honest, having looked at these numbers, I still can't actually put my hand on my heart and say I've made things better. It's fairly easy to see in some other ways, but unless I start dropping some of these, unless I go, well, I'm going to drop the worst one, then it looks okay. But if I don't drop the worst one, it fundamentally doesn't show I've made any difference. But if I take a different view of the memory allocation, and remember, memory allocation implies cache use and all sorts of other things. Reducing your total memory throughput will increase your performance because your CPU will stall less often. So in fact, you can actually quite clearly see that I've made about a 40 megabyte difference in the total allocation of ScalaC on this example, which is about 2% of all the memory allocated in the compilation. So in fact, in hindsight, I think this is a good change. I think I can demonstrate and put my hand on my heart and say, this is better than it was. But it's funny, isn't it, that you would think this would be the easy bit, right? Find a change, find something wrong, make it better, then just a quick demonstration to prove it's better. But if I remember back to the early days, I remember sitting on my machine, running the code that I've just fixed, and it's like, yeah, it's faster. And then I'd make another change. It's like, oh, that one's gone slower. Then I'd make another change. It's gone faster. Then I'd go back to this code I started with, and now it's slow again. Right? These inter-run variances are enough to make you think that you've fixed everything. Right? I've made the compiler. My first change, I would have sworn I made the compiler 5% faster. Right? I had numbers to prove I'd made the Scala compiler 5% faster. And it's taken me a long time to actually get back to the point where I actually trust my own numbers. And if you take away one thing from this talk, take away the fact that any time anybody produces a performance number, anywhere at any time, you should be incredibly suspicious of it. Right? And don't trust mine either. The other thing I want to say is get involved. I've got an incredible amount of, personally, from being involved with the community. With the guys from Lightbend, with the guys from Scala Center, with the other people in the community involved in this space. And it's not all about the compiler, as many people have already said today. It's not just the compiler, it's your entire build infrastructure. There is a lot of scope to play in this space. And when you do play, you'll learn something. And you'll learn all sorts of things. And there's more to go. There's lots more little optimizations that might make a bit of difference. There's potential for parallelization. So the back-end bytecode is being parallelized, but other phases could be parallelized. It's not, as somebody pointed out earlier, the Scala compiler, I think Julian pointed out earlier, which is the Scala compiler is mutable. And by being mutable, it's generally not thread safe. And it also does time traveling and all sorts of other fun tricks to make it efficient. By doing so, that makes parallelization a lot harder. But also one of the interesting ones, if you think back to Christoph's talk, is about bytecode generation. Is the Scala compiler actually generating the best bytecode that it can to give you the prompts, not just to the compiler, but of your apps as well? And there are lots of places to play. You can even writing a benchmark to prove or disprove how something performs, for example, the new collections, is a great help to the community as a whole. You can look at target optimization, you can look at bytecode. And it's fun. And on that note, I'm done. Any questions?
Thank you.
Hey.
So I think you kind of were touching towards the memory. So my question is, when you're running something like, let's say there was recent discussion about like what's the best way to fold option or something like that. Like some people say use maps, other people say use pattern matching or something. And when you run JMH, you can kind of see like a super micro optimization thing where the JIT kicks in and you see almost no difference or something is faster or slower. But on the other hand, one method can end up generating a whole bunch of garbage that in the context of larger, like, you know, Akka or Scala compiler, you might end up invoking like GC more often than the other solution, right? So how do you go and test it? Like, if you see more memory allocation, can you approximate that to mean that you're going to add more GC pressure that way, or?
Yeah, so this is it's a really interesting question. The question is really, I focus on memory, and I focus on memory because I found it a good indicator of what impact you have on the program. But I say functional code tends to, and this isn't always true, generate more garbage. And the interesting thing about the JVM as a whole is creating an object is basically free. Right? At the point of creation, creating an object is updating a pointer. It doesn't cost you anything. The problem is you've got a delayed cost. And in fact, you've got two costs. One is the delayed cost of garbage collecting it later. Temporary objects might push, for example, if I create a lot of small objects, what they might do is they might push stuff out of my Eden generation into the young generation. And every time you push an object up a generation, it survives a bit longer. It takes more work. And I found by reducing the Eden generation, stuff stays in Eden longer, and therefore is easier to garbage collect. So, but I think it's one of those things. I found that whichever change you make, it's, somebody used the analogy of flying a helicopter. Every input into flying a helicopter has a secondary effect. Reducing memory allocation changes your cache access patterns. It changes your memory access patterns. You know, some of the changes might have second order effects elsewhere. The other problem I found with JMH benchmark specifically is you have to be very careful about running a JMH benchmark. Because the JMH benchmark in isolation might run really fast. But then when you run it in the context of a larger project, the benefit you see might not be there. And the reason is the the Java JIT compiler is very, very smart. It goes and looks at the code that's currently loaded and says, oh, there's only one implementation of this method. And therefore, I can do monomorphic dispatch. So if you're benchmarking list.tail, it goes, there is only one tail method. And therefore, I can fast path this. This is easy. But when you load 30 other collections classes, you might find that suddenly it's gone from a monomorphic dispatch, which is incredibly fast, into a megamorphic dispatch. So those, I've yet to fully work out how to even represent that in terms of how I test things. I know Jason Zorg recently has started recommending when you run the collections JMH benchmarks, there's a JMH warm-up mode which doesn't just run your test, but it actually runs the entire suite to warm up. So it tries to load, which will push the loading of all the classes involved. And I think that's an interesting take on it. Does that sort of answer the question? Oh, one over there.
So first of all, thank you for your presentation. I found it really, really interesting. I've got this one question because you've had the slide saying that when you're doing benchmarks, there are a few things that one should take into account, like CPU throttling, right? Like the hyper-threading, that should probably be disabled when you're doing the benchmarking. And maybe you've mentioned that, and I just didn't notice it. But when I've been looking into the good tips on doing benchmarking, and as you've mentioned, I found out that there are a few things that one should check before doing the benchmarks. I've also discovered that many people mentioned turbo boosting and the changing the frequency that's being changed at the CPU level, so the clock changing the frequency. Is this something that you think that should be taken into account when doing such benchmarks?
I absolutely do. I'm just trying to find the right. So, absolutely, I think you've got to look at all the options your CPU does. Modern CPU design is a bit like JIT design. It's incredibly complex, and when we think about CPUs, we think about von Neumann architectures, right? Fetch execute cycles. And if you listen to some of the talks on what's actually going on behind the scenes, it's basically nothing like that anymore, with the pipelining and all the other things. And even just the temperature throttling that your CPU does to protect itself. And it will move code off of one core if that core's got too hot, even on singly threaded code. So it will move your code around, even if you say, lock it to this one thing, and I don't want you to do anything clever, and throttle it. So yeah, this is, I think actually trying to work out which options to set is incredibly hard, and I still continually try and update myself over what I should be doing.
Hi.
Hey.
We have a solution for tail recursion, where with annotation compiler will help us to stop compilation if method is not tail recursion, right? So my question is, can we do the same for this implicit allocation, right? Because the main problem is that this allocation is surprise. If I can annotate method and compiler will stop compilation once I have unexpected allocation here, it will be at least some sense to try to understand what's going on. Because for most cases, the problem is it's implicit, so it's surprise. So it may be a great tool to do.
I think that's a really interesting idea. I don't know of any tool that allows you to do that right now. So the idea is that you, sorry? So ScalaZ deriving is planning on doing that already. Yeah, sorry, Sam. Can you? Do you
Sam,
wanna-
could you repeat the microphone?
Yeah, so
recording?
you can only do that if you have type class coherence globally in your entire system. Because if you have one implicit derived in one part of the code and then another derived somewhere else, and they're different, then the cache could get broken. But if everything is consistent in the entire JVM, then you can just reuse one value that's created in one place everywhere. So this slide that Julian showed us in the previous talk, the deriving the thing 8 times doesn't really matter because there's only one instance at runtime, which gives huge performance benefits.
Yeah, I can't add anything to that. I think it's a great idea. You know, I think you need to pay. I think it's a great idea. I think if we did that more often, I think you would see less of these problems. And I think I've had a discussion recently with people about trying to do this around the standard collections in the 213 collections library to protect against exactly this kind of issue, so it's bounded. And just in conclusion, I just want to say, making the Scala compiler faster has been a real challenge, but in a good way. It's been really fun. You should get involved if you're not already. You'll learn something and you'll make your community better. Thank you very much.